what do we get? We solve it. The word thing is C equals, what do I have on top? Formula-wise? Q over mass delta T, right?
Oh, yeah, I have it.
Okay, all right. Yeah. Oh, yeah, absolutely. Okay. So I am trying to solve for mass, right? So I need to get that on the other side of the equation. Told you a second ago, my preference is to just go ahead and do this. And if I run it down, I'm solving for mass, I want mass equals Q over C delta T. Right now, just plug in numbers, right? It's 25,000 joules divided by 1.5 divided by 1.5. What do you get?
11,000.
11,000. What?
111.
111 grams?
Yeah, just a bunch of ones.
Okay. Good. Everybody get that? Or at least see how to get that? Okay. Do you want one more review like that before we roll on, or do you feel good? Solve for a different variable this time? Yeah? Okay. You want to make it harder or easier?
Either way.
Okay. Do harder. All right. Final temperature. So T2, right? T2 equals 26.3 degrees centigrade. Mass is 1.5 grams. Specific heat is 0.3. And what am I missing here? I need energy, my joules. So my Q is 25 joules. I want you to solve for T1. Tell me what my starting temperature was. If this were a word problem, this would be something like this: is 1.5 grams of a substance with specific heat of 0.3 rose from an unknown temperature to 26.3 degrees centigrade when 25 joules were added to the system. Determine the initial temperature. The formula is the same, right? So it's always going to be C equals Q over M delta T. Which thing am I ultimately trying to deal with here? Delta T. I have part of delta T. I have the final for delta T. So if I can solve for delta T, right, and take away my final T, that will tell me my initial T. Okay? That's how you solve this. So get at it.
How do you know if you take away a large and find there's T2?
I'm adding energy, so that's going to heat it up. If this were a negative sign, then it would be taken away. Yeah. Good question. All right, where are we? Right here, Thermochem. Okay, good. slope, T1, so T1. Sign, I should get it. What'd you get?
29.25.
What was it?
29.25.
29.25?
Negative. It's a negative.
Okay, so I think we got a problem here. So we added energy to the system, right? Which means that the temperature had to go up. So just logically speaking, T1 must be lower than T2, right? So you're saying it's negative 29.5? We had that huge of a difference?
Yeah.
Yeah. So what was our delta T?
It was like 55.
Oh, okay, all right, okay. I didn't realize it was such a large number. Okay, very good. All right, well that makes sense then. Everybody get something like that? Good, good, good. All right, well, let's dive into the next part then. We're gonna do some calorimetry. Y'all ever heard of calorimetry? Okay. The concept behind calorimetry is this. If I perform any kind of a chemical reaction, anything that has an energy change, it's often very useful to know how much energy is either absorbed or released by that reaction, okay? And so I need some way to do that. In order to do that, I've got to measure it accurately. So I don't just want to like put two chemicals into a test tube or into a Bunsen burner and throw a thermometer in there, right? I've got too many sources of error. I would be losing, if it was an exothermic reaction, it's releasing heat, I'm losing energy to the air constantly. I cannot get a valid measurement, right? So I need some system where it's insulated. And so that's the idea of a calorimeter. We take, you've got basically something like a beaker, and you put it in a box, okay? And then you'd like to get a lid on it, and you need to be able to get a thermometer in there so that you can measure that bad boy. And it's useful to have some kind of a stir to help the reaction come to completion, okay? Now, theoretically, all of the energy released by this reaction is going to remain in the liquid, right? Now we know, no matter how well insulated this is, I'm going to lose a slight amount to the external system, and I'm going to lose a slight amount to the air, right? So the fuller this is, the more accurate, the more perfect an insulator this is, the more accurate. For truly accurate measurements, you would take into account even, and we'll do a problem like this, the heat capacity of the container. You know how much it changes, okay? But this is the concept. We're having a controlled reaction where we're going to measure temperature, okay? And so we are going to do some of this. Anything else I need to say about this? No. Okay. Anything else we'll figure out as we go. Here we go. So, a 360 gram piece of rebar. $360-gram piece of rebar, which is a steel rod used for reinforcing concrete, is dropped into 425 milliliters of water, at 24 degrees centigrade. The final temperature of the water is 42.7 degrees centigrade. final temperature is 42.7. Calculate the initial temperature of the piece of rebar. Assume the specific heat of steel is approximately the same as that of iron, right? So C, somebody give me the specific heat of iron.
0.449.
0.449, what are my units? It's like joules per gram degree centigrade? Okay, good. All right. So assumptions, assume that the specific heat of the steel is approximately the same as that of iron, and that all the heat transfer occurs between the rebar and the water. There is no heat exchange with the surroundings, okay? So this is a perfect system. All right, there's several other things that we've got to know as we go about this, okay? This is essentially our same problem. We've got C equals Q over mass change in temperature, right? We are asked to solve for our initial temperature. What is T1 over here? That implies that I have T2, which I do. It's just not saying, hey, this is T2 of the rebar. But you got to think about this. Take a piece of rebar. I put it into water. It changes the temperature of the water. Is the water getting hotter or colder? Is there such a thing as colder? No, it's getting that. The water's not getting less hot, it's getting more hot. Which means, where did that energy come from for the water? From the rebar. So, the rebar, is it going to get hotter or less hot in this? Less hot, because the same measure, the same amount of energy that heats up the water had to come from the rebar, right? So my T1 for my rebar logically must be higher than my T2. The rebar in the vernacular is getting cooler, right? What is my T2 for my rebar?
42.7.
It's 42.7 because the energy will transfer completely between the two until they're in equilibrium. So T2 over here, I'm going to rewrite this. I'm going to say C equals Q over M times T1, right, minus T2, which is 42.7. This is completely valid and accurate, right? This is the same as this. Now I can fill in the rest of my variables, or I can solve this for this, right? But what variables do I know?
Specific heat and mass.
I know my specific heat. It's 0. This. Somebody's getting my good markers. I go get good markers and then they disappear. 0.449 joules per gram degree Celsius. Okay. I have specific heat. I have mass. Right? What is my mass? What is it? 360 grams? 360 grams? I've got two variables right here. I can't solve. This doesn't work. I know this is what I'm solving for, so I've got to be able to get this. I have to be able to derive this, right? So I can do that from water, right? So what's my mass of water? 425 grams. Okay, so this is it. This is just a nice thing about the metric system. 1 milliliter of water is exactly 1 gram. So it's a density thing, right? So if I have 425 milliliters, then I have 425 grams of water. Or 25 grams of water changed from 24 degrees to 42.7. What's my delta T for this?
It's 42 minus 24.
42 minus 24, what is it?
18.7.
Okay. So I've got a delta T, I've got a mass, I can get a specific heat of water, right? What is it? 4.2 joules per gram degree centigrade, right? So C equals 4.2 joules per gram degree centigrade. This is enough information for me to figure out that, right? Because the Q of the rebar is going to be the same as the Q of the water. Does that make sense? Whatever energy the rebar lost, the water gained. I can easily calculate the Q of water, right? So I'm going to take this same problem and I'm going to set it up. I know that C equals Q over M delta T. Excuse me. If I solve this for Q, then I get C equals M delta T. Of course, this is for my rebar. Sorry, I did that wrong. C times M delta T equals Q, right? Which also equals C times M delta T. So this for my rebar equals this for my water. Now I can solve it for water and I can plug back in. I'm likely to make some mistakes at that point, right? By entering and re-entering all this stuff. What I can do, I want to solve for this, don't I? So I can go C of H2O times mass, too many loops, of H2O times delta T of H2O over, solving for delta T here, so I want the C of the iron times the mass of the iron and this is going to give me the delta T of the iron. And then I can just subtract my initial and I'll have it. Does this, algebraically, does this make sense? You got all the right variables in all the right places? Okay? And all I gotta do is fill in numbers, right? So specific heat of water is 4.2 joules per gram degree centigrade times, what'd you say I had? 18.7 degrees Celsius, right? Times, I need a mass of this, right? What's my mass? 425 grams. And I divide this by the specific heat of iron, which you guys said is 0.449 joules per gram degree centigrade, times the mass of my iron, which is 360 grams, right? So these would cancel out, these would cancel out, I'd be left in degrees Celsius, which is at least the unit that I want, right? So when you run this math, what do you get? Oh, you don't need calculators. Rylan, you got yours?
Yeah.
Okay.
206.5.
206.5.
Yeah.
Somebody confirm? I know he's good, but let's still confirm it. Yeah, okay, good. Now this is delta T, but that's not what I want. I'm solving for initial T. So I need to subtract my final T from my, or I need to add my final T to this to figure out my initial T, right? And so in that case, what is this? Delta T equals T1 minus, in this case, minus T, or know that we're going lower, right? So I've got delta T in this case equals T1 plus T2, yes? Okay, so what is, so I've got my delta T is 206.5, right? If I then, that's wrong. If I then add my, what is it, 18.7? 18.7 degrees Celsius.
Is 42.7. 42.7.
42.7, okay, thank you. That was for the water, right? Okay, 206.5 degrees Celsius plus 42.7 degrees Celsius, what do you get?
249.2.
Is it 249.2?
Yeah.
Okay, we're within one of what it says the right answer is. Good, good, good. Okay. That seemed like a lot of work, didn't it? Probably need a little more practice with that. Let me erase all this. Do another one. Probably the big thing to look over in this is that when you're doing a calorimetry, you're always going to be able to determine the amount of energy, because that's ultimately what you're looking for by looking at the change in the water, okay? So I can solve for my Q from the water, and then I can plug that into the other side, and that will tell me, you know, whichever, that'll let me get at whichever variable I'm missing that I'm trying to solve for. Let's do this next problem. A 248 gram piece of copper. So 248 grams of copper is dropped into 390 milliliters of water. At 22.6 degrees centigrade. The final temperature of the water was 39.9 degrees centigrade. Calculate the initial temperature of the piece of copper. Okay, so it's essentially the same thing all over again. I've got specific heat equals Q over M delta T, right? I know that this is going to be the same for both the water and for the thing, right? So I want to set my equation equal to Q. So I go C M delta T equals Q, right? So I can set both sides up with their information for that. Specific heat of copper, what is that?
0.385.
0.385 joules per gram degrees centigrade, right, times a mass of 248 grams times temperature. Well, we're solving for delta T, right? Times delta T equals, and then over here it's going to equal the same thing. So my mass is how much? 390 grams. And my specific heat is 4.2 joules per gram degrees centigrade. And my delta T I can solve for here, right? So it's what, 17.3? Does that seem right? So I'm just looking to solve for this. To do that, all I need to do is divide by this. So I'll put a line here, and I'll go 0.385 joules per gram degrees centigrade times 248 grams. Do me a favor, put your pencil down. It's a good point to just check and see, are we even on the right track, okay? So we set this up. This was C, M, delta T that I'm solving for. Here's C, M, delta T that I have, okay? To solve for this, I've got to divide both sides by this. So I put 0.385 joules per gram degree centigrade and 248 grams over here, so delta T equals this. Now, this would cancel out, this would cancel out, it would leave me in degrees centigrade. It's going to be my delta T, which is not ultimately what I'm looking for, but I'm in the right unit, so I know I'm on the right track. So I want to solve for this, and then figure out, I know what my final one was, I can figure out my initial one, right? So do me a favor, get me the delta T right now.
$296.79.
296.79 degrees centigrade, right? Okay. And my water got hotter or colder? Hotter, which means my copper got hotter or colder?
Less hot.
Less hot. So the temperature went down. So I need to add or subtract this from my delta T. Right? Will I add or subtract this value? I'm going to add it. Right? So 296.79 degrees centigrade plus 39.9 degrees centigrade equals Can you say it again?
336.69.
69. Let's see if that's the accepted value. I don't think it is the accepted value. What have we been using for the precipitated water?
4.2.
That's where, okay. We need to be using, that is a generalization that the book gave you, by the way. But we need to be using 4.184. So that is why our numbers are off, and the bigger the... So we're going to do this. I want you to run that number again, but we're going to use 4.184. Okay? And tell me what you get. That's going to change our delta T, which will then change our final number.
About 345.56. Oh, no, for the final.
Okay, give me my delta T first.
295.6.
295.6?
66.
0.66? Okay. 295.66 plus 39.9 equals
335.56.
0.56, and that is the right number. Okay, good. Good. Do you want one more like this, or can we roll? Yours good? Okay. All right. It does occur to me, I have not prayed for us. I have not prayed for me. Probably should, so let's pray. Father, help me to present this material clearly in a way that's just easily understood. Help it all to be clear in my mind and help me to be effective in the teaching. And help our students to understand what they're seeing and to understand what they know and what they don't know, to ask questions where there's a difference. Their mind to be sharp and to retain this information well for your glory and their good. We pray in Jesus' name. Okay. So it says here a 59.7 gram piece of metal. 59.7 gram piece of metal. Right now this has me very suspicious. I'm automatically thinking it's probably going to want me to solve for it. Didn't tell me the metal, which means it probably wants me to find the metal, right? Which means I'm probably going to need the specific heat. I could be wrong, but we'll see. 59.7 gram piece of metal that has been submerged into boiling water. So what do I know about this water? What temperature is that? 100 degrees centigrade. Is quickly transferred into 60 milliliters of water. Initially at 22 degrees centigrade. The final temperature is 28.5 degrees centigrade. Use these data to determine the specific heat of the metal. Okay? So let's go back again to our formulas. I know that C equals Q over M delta T. Right? So I'm solving for this specific heat, but if I will just set for Q first, I can really do something with that. So I go C M delta T equals Q, right? That's a mess. Yes, so if I will just solve for Q on both sides, then then it will be equal, so I can go equals C M delta T, right? Now I'm looking for the C of this one. This is the C of my unknown metal. So my new formula will be, I'm going to do 4.182 grams, or I'm sorry, joules per gram degree Kelvin. That's a specific heat of
184. 184.
184.
Water.
I got it from 4.182 everywhere.
Water?
Yeah.
Oh, mine's is water.
Yours says 184?
Yeah.
Okay.
Yeah,
Let's
it's
do that.
184 too.
All right. I may have been doing it wrong. Okay. Specific heat of water times the mass of water. What's my mass of water? 60 grams. Times my delta T, which is 6.5, right? And now I want to put this over, I'm solving for C, right? So I want to put over mass times delta T, the metal. The mass of the metal is 59.7 grams. And the delta T of the metal is 71.5 or something like that. Don't trust me, I'm not trustworthy on math. 71.5 degrees centigrade, right? Just checking this hypothetically, these would cancel. These would cancel. Would leave me with the units for specific heat. Algebraically, this looks great, right? Of course, I know that this is specific heat of water. I'm going to just circle my different units. So this is water. This is for the water. This is for the water. This is for my iron. This is for my iron. And this equals the C of iron. Or of, I'm sorry, not of iron. I'm assuming it's iron. It's not going to be iron. C of whatever my metal is, right? So if I solve this, I should get the specific heat of this metal. I can compare it to that chart, and I'll know what metal it is. So go ahead and get after it. Got it, call it out, Jimmy.
I think it's copper, because the
What-
number is closest to copper.
Give me the specific heat first.
It's 0.3822.
0.382.
Yeah.
Okay, good. And you think it's copper?
Yeah.
Yeah, that looks good. Looks real good. Yes, go ahead. I'm in class. I'm in class. It's okay. She never calls when I'm in class. She has my schedule, so she doesn't call in class. So when she calls, I'm like, well, this must be serious. So sorry to waste your time. You'll have wives or husbands someday, you'll understand these things. All right, so this is good. That's great. Y'all ready for the follow-up problem? Check our learning? Okay. All right. A 92.9 gram piece of silver gray metal, so 92.9 grams of a metal, is heated to 178.0 degrees centigrade. Okay, and then quickly transferred into 75 milliliters H2O at 24 degrees centigrade. After 5 minutes, both the metal and the water have reached the same temperature of 29.7 degrees centigrade. Determine the specific heat and the identity of the new metal. Right? So it's, I mean, literally, this is everything's the same. The numbers are just different. C equals Q over mass delta T. Right, so Q equals C M delta T. So C M delta T equals C M delta T. Right? And now I want to solve for C over here. So I get C equals Cm delta T over M delta T, right? My water's up top, my metal's on bottom. All I have to do is plug those numbers in and I am there. So my C equals 4.182, you said?
Yeah.
Joules per gram degrees. 84, I keep doing that, don't I? 4.184 joules per gram degrees centigrade times 75 grams times change in temperature is what, 5.7? And divide all that by 92.9 grams times whatever that temperature change is. That's going to be 147.3 or something like that?
148.3.
148.3? Okay. These will cancel. These will cancel. Leave me with a specific heat. As long as I entered my calculator right, I know I'm there. Again, please do not take for granted. Always run your numbers at least twice. If you get the same answer twice, you're golden. If not, run it again. So what do we get here?
I got 0.1298.
0.1298. Can I get a confirmation?
Yeah.
Good. Okay. So now let's look at our chart and tell me what metal that is.
Gold.
Gold. Here's the one thing. They said it's a silver gray metal. So we're going to have to dismiss gold, even if it's the closest. What's the next closest? Lead. Okay. And that now makes sense why they told us it was silver gray. Because we would automatically hone in on gold. They want you to use other senses. So, all right, everybody feel good? Good. All right, let's do the next one. What time is it?
122, 23. 120.
120? I thought you said 1.3 or something. Like we're giving time in decimals now? I'm
120.
not going to make it. All right, good deal. Okay, so when 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar, sorry, it's 1.00 molar, I shouldn't be cutting corners there, 1.00 molar of both. 1.00 molar NaOH. These are both aqueous, I skipped that also. Okay. Are added to a coffee, both at 32 degrees centigrade. They're added to a coffee cup calorimeter. The temperature of the mixture reaches a maximum of, sorry, I'm blind. That doesn't say 32, that says 22. The temperature reaches a maximum of 28.9. Okay. So it's heating up, right? This is an exothermic reaction. What is the approximate amount of heat produced by this reaction? Okay. So I've got my formula. Let me write down. I want to know how much heat, how much energy, right? So which my variable I'm asking is asking me to solve for? Q. I want to know what Q is. Okay. So my formula says C equals Q over M delta T. I know I'm solving for Q, so I know Q equals C M delta T. Right? Okay. So that we can start putting some stuff in here. Q, I don't know. Specific heat. Specific heat of what? Water. These are that's part of why it's telling us aqueous. These are aqueous solutions. So this is all happening in water, so I need the specific heat of water. Right? So Q equals 4.184 joules per gram degree centigrade times the mass of water. How much water? 100 milliliters. Because I got 50 milliliters of one substance and 50 milliliters of another. If you mess that up, you'll have half of the value that we want, right? So that is an important thing to catch. 100 milliliters of water or 100 grams of water. Okay? Now, my change in temperature is 6.9. Now that becomes super easy, right? Solve for Q. What'd you get?
2,886.96.
Okay, you got 2,000 what?
886.96.
86.96. Okay. We're limited to 2 sig figs because of 50 mLs, right? I don't have a decimal anywhere or anything like that. So I need to put this down to 29, right? 29,000. Or I could, I could say, or 2.9 times 10 to the third. Or I could say, and this is how they're ultimately wanting this, 2.9 kilojoules. Although, other than this one's not right because it's sig figs. The rest of these are all saying the same thing, right? Okay. The only reason I would care about anything is if I told you to put it in one or the other. All right. And I would tell you, I wouldn't do that to you. Very good. Let's do another one. When 100 milliliters of 0.200 molar NaCl and 100 milliliters of 0.200 AgNO3, these are both aqueous. Are mixed. They're both at 21.9 degrees centigrade. They're mixed in a coffee cup. The final temperature is 23.5 degrees centigrade. A solid silver chloride forms. How much heat is produced by this reaction? What assumptions? We're not worried about what assumptions. I want you to solve for the heat, right? So solve for Q. Right, so again, formula C equals Q over M delta T. We want to solve for Q, so Q equals C M delta T. What's my specific heat here? 4.184 because it's water. What is my mass here? 200 grams, because I'm adding these two things together, and my delta T is whatever that comes out to be. Okay, so I put this whole thing together, and I get Q equals 4.184 joules per gram degree Kelvin times 200 grams times, what did you say this was?
1.6.
1.6 degrees centigrade, and what's my answer?
It's 1,038.88.
1038?
1338.88.
Oh, 1338.88. That should be joules, right? Okay. Pretty good. All right. Awesome. Okay. Next one. When solid ammonium nitrate dissolves in water, the solution becomes cold. This is the basis for an instant ice pack. So this, like, you get a sprain or something like that, and they just give you this packet of white thing, and they crush it and they put it on you. What's happening there is you've got ammonium nitrate, which is used in fertilizer and balms. When it dissolves into water, it absorbs water from, or heat from the water, and so the water becomes less hot. So here we go. So we've got 3.21 grams of solid NH4NO3. Okay. It dissolves into 50 grams of H2O at 24.9 degrees centigrade. The final temperature is 20.3 degrees centigrade. Okay? And so what's it asking you to solve for? Calculate the Q for this reaction. Okay? On here. Okay. So far, when we've been dealing with our masses, we've been dealing with the mass of an entire solution. Okay, it's been 50 grams of this solution. The solution contains the solute and the solvent. Okay, so a certain portion of that would be the water. A certain portion of that would be the potassium chloride or whatever it is. In this case, it's giving me solute and solvent and saying, hey, we're making solution. So how much solution am I making, mass-wise? 53.21. So I need to account for that. So this is 53.21 grams of solution. Now we're going to do everything else for just pure water, but we don't want to miss this step or we'll be off by 6.42% or something of our answer. So I've got the specific heat of water times the mass of the solution, right, times the change in temperature. And this change is going to be positive or negative?
Negative.
Negative. We're getting colder, right? So it's negative, getting less hot. So it's negative, what, 4.6?
Yes.
Okay. Which means, think about this. Q of the system is going to be negative sign, right? Because we're getting colder, so to speak. So this makes sense. When I multiply this out, my grams will cancel, my degrees Celsius will cancel, I'll be left in joules. That's exactly what I want. When you run this math now, call it out when you get it, please.
1024.1.
1024.1 negative, right?
Yes.
Joules. Okay. Check and see if that's right. That is right. Now, all right. They want it in the proper sig figs, which is going to be 3, from what I can tell. Right. So why do they have it the way they have it? I don't know. They're just calling it 1.0 kilojoules. Still seems like it ought to be 1.02 kilojoules because we have 3 sig figs everywhere. All right, but our math looks good. One more like this one. Times it now?
137.
137. You ever wonder why I ask that so often or check my phone so often? There's always this ticking in my head saying, you're behind, you're behind, you're behind. And I don't know. And then I'm fighting that. It's like, I don't want to just leave everybody in the dust, but. 1.33 kilojoules. Oh no, that's I'm sorry. All right. 3.00 grams of KCl. So potassium chloride was added to 3.00 times 10 to the second grams of H2O in a coffee cup calorimeter. The temperature decreased. So that gives me a delta T, right? They didn't give me an initial and a final. They gave me a delta T. Decreased by 105 degrees centigrade. Or 1.05 degrees centigrade. How much heat is involved in the dissolution of KCl? I want to solve for Q, right? Well, that's easy, right? We can do that. So it's Cm delta T. Is this one there? 4.184 times, what's my mass?
303 grams.
So 3.00 times 10 to the second. So I move this over, so that puts me at 300, just in case we wasn't catching that right away. And I add that, so 303 grams. And I multiply that by my delta T, which is 1.05 degrees centigrade. Now, this is positive or negative?
Negative.
Negative. Okay. So what do you get?
$1,331.14 negative
Negative 1,300 and what?
31.14.
31.14 kilojoules. Right, using sig figs, I'm allowed 3. So I get 1,330 kilojoules. Joules. You gave me joules, not kilojoules, right?
Yeah.
They keep wanting everything in kilojoules, so I'd get 1.33 kilojoules. All right. Let's do the next one. Okay, this is now, the last couple were in what we call coffee cup calorimeters. We weren't being overly precise. I mean, literally, like in a lab, you do these with a styrofoam coffee cup, okay, and a lid. The next one is dealing with, we need precise details. And so in this one, we're gonna have to account for the specific heat of, and the mass and all of the calorimeter itself. This is what's done in what's called a Baum calorimeter. It says when 3.12 grams of glucose, C6H12O6, is burned in a balm calorimeter. The temperature of the calorimeter increases from 23.8 degrees centigrade to 35.6 degrees centigrade. The calorimeter contains 775 grams of water. That water went from 23.8 degrees centigrade to 35.6 degrees centigrade. The calorimeter contains centers, and the balm itself has a heat capacity of 893 joules per degree Celsius. Okay, so that's how much energy it takes to raise that by. So every degree that this would raise, I'm going to have to multiply it by that to figure out the amount of energy that the balm calorimeter itself took up, right? So whatever this is, the delta T here, I multiply it by this, that'll tell me how much energy that, I'll have to add that to the energy of the water to figure out the total energy. Make sense? Yes or no? Let's just do this. Q of reaction is going to equal the Q of the water plus the Q of the calorimeter. Okay? So I'm doing a double solution. This is not hard, right? I can find the Q of the calorimeter simply by multiplying delta T times heat capacity, right? This one I do by solving the normal formula, right? C equals Q over M delta T. Add those two together, I'll get the Q of the reaction, right? So let's put that in a simpler way. Q of the reaction equals C of H2O times mass of H2O times delta T of H2O plus 893 joules per degree Celsius times delta T of thing. And that will give me the Q of the system, or of the reaction. Right? So let's start plugging numbers in here. So the Q of the reaction is 4.184 times 775 grams times, what is this delta T? 11.8 degrees Celsius plus 893 joules per degree Celsius times 11.8 degrees Celsius. When I plug that, I'll have the right number. And let's make sure that all our units cancel. I'm looking for joules. This will cancel, that'll come out in joules. Oh, this is joule per gram degrees Kelvin, or degrees Celsius. These will cancel, that'll leave me in joules, which is the unit that I want. I can't stress how important it is to check those things, just to see if your answer is going to be reasonable. Are you on the right track, or do you have to start back over? Yes, sir?
You don't need to add the grams of into the solution.
No. No. I should not, because that is not dissolving, that's burning. And so it's not adding to the mass of the thing. The only thing that's happening is that heat transfer. So this will be happening basically in the air above the water. The water is going to change temperature. Let me confirm that I'm not dumb. I might still be dumb, but let me confirm that I'm not wrong. They said it the same way I did. You got it?
Yeah.
What is it?
14,240.24.
Whoa, 14,240 point what?
24.
0.24. Let's put this in the proper sig figs. How many am I allowed to have at most? 3. So this is going to be like a 14200, right? If I were to put that in scientific notation, or at least in kilojoules, which they seem to want, I'd probably have 14.2 kilojoules, right? Let's see what they have here. That is not the answer they got. Did you get 48.8?
Yeah.
Yeah, okay. We just got a number off somewhere.
Oh, yeah.
.8 kilojoules. All right. Okay. Let's do the next one, which is also the last one of this portion here. Which lines up at a time. We're going to do this last problem. If you got to go, go ahead and go. If you can stay, please stay. Here we go. When 0.963 grams of benzene, that's C6H6, is burned in a bomb calorimeter, the temperature of the calorimeter increases by 8.39, so I've got a delta T. Delta T equals 8.39 degrees centigrade. The bomb has a heat capacity of 784 joules per degree centigrade and is submerged in 925 milliliters of water. Wow. How much heat was produced by the combustion, right? So the Q of the reaction equals the Q of the water plus the Q of the calorimeter, right? So I need to count for both of those. If I want to solve for Q, Q equals Cm delta T. If I want to solve for joules here, Q equals 784 times delta T. Of the calorimeter, this is the Q of the water, right? And so this should be easy. This should be straightforward. What do we have here? 925 grams times delta T is 8.39 degrees centigrade. Add to that 784 joules per degree centigrade times 8.39 degrees centigrade, right? When you get this number, would you call it out to me?
3.9 kilojoules. 3.9 kilojoules.
3.9 kilojoules. You're off by a factor of 10.
So it says 39.
Huh?
39.
39 kilojoules. Now the thing is our sign, so this is an exothermic reaction, right? So it's going to put off negative 39 degrees temperature. And that just comes down to just knowing your slide. All right. I will see y'all in 2 days.